All right, welcome back, everyone, to The Deep Dive. We're diving into a fascinating development that could be a total game changer in the world of AI hardware.
Oh yeah, this is a big one.
Straight out of Columbia Engineering, their researchers have created this, well, it's a brand new 3D chip, but it's not just any chip, it's a photonic-electronic chip. And get this, it's specifically designed to tackle one of the biggest problems holding back AI. The huge energy consumption of moving data around.
That's exactly it.
Yep.
You know, all this incredible progress we see in AI, pushing the limits of what's possible, it all depends on being able to handle mountains of data.
Right.
But shifting all that data around, it eats up a ton of energy.
Yeah.
So it creates these bottlenecks that really limit how fast and how big these AI systems can get.
Yeah, you hit the nail on the head there. So with us today, we're going to take a deep dive into this new technology. We want to understand how it actually works and why so many experts think it's a huge leap forward, not just for AI, but for all sorts of computing applications that, might actually impact the technology you and I use every single day. We'll be digging into the juicy details from the Columbia Engineering report.
Yeah, and this isn't some, pie-in-the-sky idea. This is the real deal. This is groundbreaking stuff published in Nature Photonics, one of the most respected journals out there.
Okay.
March 21st, 2025, that's when it dropped. And if you really want to go down the rabbit hole, the DOI is 10.1038S41566-025-0163330.
I'll put that in the show notes. So the brains behind this, we have Karen Bergman at Columbia Engineering,
Right,
and Alyosha Christopher Molnar from Cornell University working together on this. Okay, so let's break this down. What exactly is the big innovation? What did they do differently that's got everyone so excited?
Well, the magic lies in how they've woven together two different technologies onto one 3D platform. So they combined photonics, which basically uses light to transmit data, with the good old CMOS electronics, the foundation of most digital devices we use.
Sure.
Now, the real breakthrough is how this combination, it unlocks all these new possibilities for moving data around.
Okay, so instead of just relying on electrical signals to move data within the computer, they're using light for some of the heavy lifting.
Exactly. And this switch to using light, it offers some incredible advantages. First off, you get a massive boost in energy efficiency for data transfer. Like imagine finally breaking through this energy barrier that's been holding back computing for ages.
Whoa, energy barrier. That sounds like a big deal. I mean, we're not just talking about slightly reducing power consumption, are we?
No, not at all. This has huge implications for the kinds of AI systems we could be seeing in the future. And then there's the tremendous increase in bandwidth density. Picture it like, turning a narrow country road into a multi-lane superhighway. You can move so much more data along it at the same time, all within the same physical space. And to really drive home the significance of this, let's hear directly from Karen Bergman, the lead researcher. She said, and I quote, "In this work, we present a technology capable of transferring vast volumes of data with unprecedentedly low energy consumption. This innovation breaks through the long-standing energy barrier that has limited data movement in traditional computer and AI systems."
Wow, that's a powerful statement. Okay, so let's get into the nitty-gritty. What kind of numbers are we talking about here? What's the proof in the pudding that this is a giant leap forward in data transfer?
Well, the numbers are really impressive. This single chip packs in 80 photonic transmitters and get this, 80 receivers.
80.
Yeah, that's a lot of light-based communication channels crammed into a tiny space, all working together. This allows the chip to reach a bandwidth of 800 gigabits per second.
Whoa, 800 gigabits per second. That's a fire hose of data every second.
It is. And the energy efficiency, that's where it truly shines. They've managed to hit an unbelievably low energy consumption of just 120 femtojoules per bit.
Okay.
Now, a femtojoule is, well, it's a tiny fraction of a joule. So this represents mind-blowing efficiency. Think about it. Current systems might guzzle hundreds or even thousands of femtojoules to move a single bit of data. So this isn't just a minor tweak. It's a potential game changer that could completely transform the power needs of the next generation of AI.
Right.
But wait, there's more. The bandwidth density, it clocks in at a whopping 5.3 terabits per second per square millimeter. Now, bandwidth, think of that as how much information can flow at once. And density is basically how much of that flow you can pack into a small area. 5.3 terabits per second per square millimeter, that means they've created this incredibly efficient information superhighway, all squeezed into a minuscule space, way beyond anything possible with current technology.
Okay, so these numbers, they're definitely impressive. But a lot of times, this kind of bleeding-edge tech, it comes with a hefty price tag, and it's a nightmare to manufacture at scale. How does this chip stack up on that front?
Yeah, that's a crucial point. And the researchers, they definitely thought about that. Their design is all about using commercially available components, things you can find readily. By cleverly integrating those advanced photonic devices with standard CMOS electronics, the workhorse of today's chip industry, they're aiming to make this technology both cost-effective and easy to integrate into existing manufacturing processes.
So it's not just about creating something super powerful in the lab. It's got to be something that can actually be mass-produced and put into the real-world systems that, you and I might be using indirectly.
Precisely. It's all about making it practical and widely applicable. And when you zoom out and look at the big picture, the implications for AI infrastructure, they're huge. Remember, energy efficiency and the ability to move tons of data quickly, those have been major roadblocks in AI development. And this technology, it tackles them head-on by making it possible to efficiently move huge amounts of data between all the different processing units.
Oh, so this could really pave the way for more distributed AI architectures, systems that aren't limited by, how fast and efficiently data can move around inside a single machine.
Exactly. It unlocks this whole new world of possibilities for building and using AI models that require massive data sets and incredible processing power, things that used to be held back by energy consumption and those annoying latency issues.
Now, the report also hints that this tech might have applications beyond just AI. Where else could this kind of breakthrough in data transfer really shake things up in ways that you and I might be interested in?
Well, that's a great question. And the answer is, the potential is pretty vast. Yeah. Think about high-performance computing, where you absolutely need to move massive data sets around super fast for complex simulations and scientific number crunching. This could be a game changer there. And then there's telecommunications, where we could see a giant leap in network capacity and efficiency.
Yeah, faster, more energy-efficient communication networks. That would touch just about every technology we rely on these days.
Absolutely. Then you have these things called disaggregated memory systems. Imagine instead of every computer having its own fixed amount of memory, you have this shared pool of memory that any computer can tap into whenever it needs. Oh. Now, for this to work smoothly, you need incredibly fast and energy efficient ways to move data between the processors and this memory pool. That's where this chip could really shine. We could also see big strides in real-time data processing, which is essential for stuff like self-driving cars that need to analyze tons of sensor data in a split second. And of course, as we've already talked about, it could make it possible to train and use much larger and more complex AI models than we can even dream of today. I mean, who knows? Maybe this is the key to finally unlocking the true potential of self-driving technology, the kind of stuff we've been hearing so much about.
It sounds like this improvement in data transfer is like this fundamental building block that could push progress across a bunch of different fields.
Exactly. It's about overcoming a key hurdle that's been holding back advancements in, well, pretty much every area of computing and information technology.
And it wasn't just the Columbia team on this one, right? There were other institutions and researchers all collaborating on this.
Oh, absolutely. It was a big team effort with some key contributions coming from Alyosha Molnar's lab over at Cornell University. And we can't forget the Air Force Research Laboratory and Dartmouth College. It really highlights just how complex these challenges are and the need to bring together experts from all sorts of disciplines.
And it sounds like this project gets some serious attention and backing from some big government agencies, right?
Yeah, absolutely. The fact that it snagged major funding from DARPA, the Defense Advanced Research Projects Agency, and RPE, the Advanced Research Projects Agency Energy, it tells you that this is seen as a pretty big deal for national technological advancement. Things like strengthening defense capabilities and boosting energy efficiency.
So just to recap for everyone listening, we have this incredibly innovative 3D photonic-electronic chip developed by a talented team of engineers at Columbia working hand in hand with researchers at Cornell and other institutions. This represents a huge step forward in addressing the energy-guzzling problem of data transfer. It achieves this by combining light-based communication with traditional electronics in a super clutter and efficient way.
And the potential impact of this, it's massive. We're talking about a fundamental improvement in how we move huge amounts of data, making it faster and more efficient. This could revolutionize AI, high-performance computing, telecommunications, and a whole bunch of other data-intensive technologies that will probably touch your lives in the coming years.
Think about some of those cutting-edge areas that you're probably already interested in, like even more advanced self-driving cars that need to process tons of sensor data in real time,
Right.
or those increasingly complex and powerful AI models we're hearing so much about. This type of technology could be the key to unlocking the next level of progress in all these areas.
And that brings us to a really thought-provoking question for everyone listening. Looking beyond the immediate applications in AI and computing, how might this fundamental shift in data transfer reshape industries and technologies that we haven't even dreamed up yet? By shattering this long-standing energy barrier in data movement, what entirely new doors are now open to us? It's definitely something to ponder.
It really is food for thought. Well, that's all the time we have for the deep dive today. Thanks for joining us. Until next time, keep exploring.
Absolutely. Keep those brains buzzing.